All right, so review 1, number 15. And again, if you see something, yeah, there's even an uglier one than this on the back of review 2. So there's a couple ways you could go about this. I know that I've told you when there's a fraction inside of a fraction, what can you do? What was the little shortcut I told you? I do it all the time. You will eventually begin to do it all the time. But things like when you have a fraction inside of a fraction, what can you do as an alternative to actually finding a common denominator and adding that, finding a common denominator and adding that, and then to divide by a fraction, multiply by a reciprocal? What's an alternative?
You can multiply everything by a common denominator of all of them.
Multiply the top and the bottom, or basically every term, by the common denominator of all the terms. So in this case, the common denominator of all the terms would be what? Can you see it?
60?
60? And again, if you don't see it, remember what we do? We take the highest power of all the prime, if we look into the prime factorizations, highest power of everything. So there's a 2, but there's a 2 squared. There's 1, 3, there's 1, 5, that's 60. So I'm going to multiply the top by a 60 and the bottom by a 60. And when I do that and distribute it through, I get half of 60, a third times 60, a fifth times 60, and a fourth of 60, which just gives me 10/27. And that's just so much easier, I think, than finding two different sets of common denominators and dealing with that. So I'm going to have that approach here, except what's even harder about this one?
It's got a second fraction in the numerator.
It's got a second fraction within the fraction, right? Well, when you think about PEMDAS, it says parentheses, right? So if you look at this and you go, oh my gosh, I've got a fraction inside of this fraction, and then I've got another fraction inside of this fraction. Well, take them one at a time. Let's just think about just this one. What would be the common denominator of all three of those terms? X, right? So what if I multiply just this, the top and the bottom by an x? I'm going to bring everything else over. So I'm going to bring over 1 minus, and on the bottom, 1 minus. And I'm concerned with just this fraction now. So when I distribute that in, what do I get? X times 2, x times 1 over x, and then here, x times x. Okay, well now I've got just fractions inside of fractions now. And then I do it again. Now I'll show you another way to do it. If you don't like this, I get it. I'll show you another way. But right here, now I can look at it and go, now that I have just a fraction inside of a fraction rather than a fraction and a fraction and a fraction, now that I have it to kind of like the problem I did before, which is 1/2 and 1/3, what would you multiply now by?
X squared.
X squared. So because that's a 1 on the bottom, x on the bottom, x squared. So x squared on the top and the bottom. And when I distribute that in, here it gives me an x squared. Here it completely cancels. Why is this wrong what I'm writing right now?
Because you have to distribute.
Yeah, because that's going to cancel. I'm going to go negative all of that. Don't forget to change that sign. And then x squared times 1. And x squared times that. One of the x's cancel, leaving me a negative x. Now I have a question for you. Should I even bother trying to factor this? Because remember, PEMDAS, simplify means PEMDAS. There's no F in PEMDAS for factor. Should I bother?
Yes.
Why?
Because you could divide. There can be subject to.
So it's possible, I know when I factor this, I'm going to get a couple binomials, right? And if I factor an x out of this, I'll have a monomial, but a binomial also. And there's a chance those binomials may match. So I'm going to go ahead and factor just to see. But like if all I had was an x squared on the bottom, I'm not factoring this. Because there's no way binomials are going to cancel with the monomial. It's not going to happen. But look, this actually factors into x minus 1 quantity squared. And if I factor an x out, I get an x minus 1. So it turns out one of those x minus 1s does cancel. Now, if you look at this and you hate this, then do this instead. I'll leave that up there. Do this. How How do you subtract that? What would you do if I just wanted to go 2 minus 1 over x? What would you have done?
Multiply the 2 by x.
Can I just randomly multiply it by an x?
No.
So put it 2x over x. And then what do I have now?
Common denominator.
So 2x minus 1 over x, right? That's finding the common denominator. So what I could have done is 1 minus, that becomes 2x minus 1 over x over x over 1 minus 1 over x. Now, how do I take this fraction and divide by a number? You multiply it by its reciprocal, and that gives me 2x minus 1 over x squared. Now I have 1 minus 2x minus 1 over x squared all over that. Well, that's the same place I am, right in the blue there. Now, if you still don't like this fraction and the fraction stuff, what could I do? I could change that 1 to what? X squared over x squared. And I could change that 1 to x over x. And I could subtract this. And I would get x squared minus 2x plus 1 over x squared all over x minus 1 over regular x. And then how do I divide by a fraction? Multiply by the reciprocal. And then at that point, I would have to factor this, and I could cancel one of those, cancel one of those, and I'm left with x minus 1 over x. So you can do it the old school way, but just keep in mind, I had to find a common denominator, add, divide, multiply by reciprocal, get another one, find more common denominators, get together, then multiply by reciprocal here, multiply through by an x, multiply through by an x squared, and I was already there. To me, it's a little simpler that way, but if you don't see it, hey, stick to what you know. Okay, that's 15. Look at 22. And again, if you're good on all this, do your thing. It's fine. Okay, it says your mama is trying to make a perfect sweet tea. All right, she has a 20-gallon container. It is currently full, already full. So a huge container, completely filled to the rim with 20 gallons of a 5% sugar solution. So what was my hint to you when you're doing these mixture problems? Think about it like a what?
Fraction.
Amount times a percent. Because it's almost like a rate times time. It's amount, percent. So I have an amount times a percent. So I currently have a 20-gallon container that is a 5% solution of sugar. That's what I have. Now, what does it say? It says I'm going to drain something off. So I'm basically going to pour out a certain amount. Does it say how much I'm pouring out? So I have no idea what I'm subtracting. So I'm subtracting amount, but I'm also subtracting an amount that has a certain percentage associated with it. What is that percentage? Careful, I got a completely full container of tea, right? When I dump it, what is leaving? What's leaving is what's in there. Are y'all with me? Like if you have a gallon of Milo's tea that's like super sweet, when I pour it out, am I pouring out unsweet tea? No, I'm pouring out what's in there, right? So when I drain it out, I'm losing the percentage that's already in there. I just don't know how much I'm losing amount-wise, but that's the percentage that's leaving. Does that make sense? Now then it says, I'm going to replace it with a 12% solution. So I'm adding back in another amount, which has a certain percent. So what am I adding back? I know it's a 12% because it tells me a 0.12 is what I'm adding back, but how much am I going to add back?
The same amount you drain.
It would have to be the same amount I'm draining out if I'm going to end up with 20, right? I mean, if I drain out a bunch, I'm going to have to fill it back up to the rim to end up with the same amount that I started with. So I'm going to add back the exact same amount. It's just going to be more sweet, right? So I'm draining off some of this unsweetened or not sweet enough so that I can add super sweet tea back in order to raise the overall sugar content from 0.5 to what? So I'm going to end up with a total amount or final amount and some weighted average in between that 5 and the 12, which looks like it's what? 8%. But how much?
20.
Back to 20, which makes sense because this amount, first amount, minus second amount, plus third amount, all these amounts have to add to 20, and they do, 20 minus x plus 6. Now I can't imagine it getting any harder than that. I mean, there's a lot going on in that thing, right? Y'all with me? And a lot of times on a test, I'll say, set up what you would do. Well, you've done that. You've set it up. I don't need to see anymore on a test. What would you do, though, if you were solving this?
Multiply 2 by 10. Get rid of decimal.
Would 10 do it?
No, 100.
Yeah, you did 100 on this one. So if I multiply that by 100, I get 5, 5, 12, and 8. You don't have to, though. I mean, you might not be super comfortable going that times that and getting 1. A lot of people aren't, including me. I'd rather say that times that is 100. But that right there times that is 1. And that right there times that is, what, 1.6? So you could do it, but most people I find that a little bit more comfortable dealing with whole numbers. What you thinking? So far so good? But be prepared to see those word problems, and if I just say set up only, don't solve them. You're wasting your time.
Are most of them just going to be set up?
I do that a lot because if you set them up incorrectly, then you're going to be solving an incorrect problem. It just snowballs. It makes it harder for me to give you partial credit. But if I just say set it up, and then I can turn around later and give you an algebra problem like this for you to solve, and that way your mistakes don't snowball on you. And that's 22. Look at 28. Okay, Biff paints up 20. Okay, there's a lot of ways to do this. I used to think there was just kind of one way, and but I've since seen lots of different ways from my students, and that's why I now think there's lots of different ways. And some of the ways that they did it, actually, I liked a little bit better. So if you remember back to what we did, that very first pump problem, if I told you how long it took for a pump to complete a task, it's not just the hours, but we could use that hours as a what? Do you remember? As a rate. So right here it says Biff, by himself, can paint a house in 20 hours. So that's great news for Biff, I guess. I mean, I would love to be able to knock out a whole house in 20 hours, but I also get a rate from that. So I know that Biff can paint 1/20th of his house, right? If he could do the whole house in 20, he could do 1/20th per unit of time. Now Barbie, on the other hand, says it does not give her a rate, does it? So it does not tell you how fast that she can do it, but you do know that working together, and if you remember the first pump problem we did, I gave you the hours of each, so you knew that, but this one I didn't say how long Barbie could do it working by herself, so I don't know that number. I don't know that number that goes down in the denominator. So I'm going to start like this and say, I don't know that number, X or whatever you want to call it. Okay? And this is probably maybe a little bit easier for you to think about. And then it says, however, the two together can paint the house in 8 hours. Now, if you remember correctly, if you remember about that original pump problem, in the pump problem, I knew how long they could do it individually, and I was solving for how long. Are you with me? I was trying to find how long it could take them working together. But I know that number. Are you with me? So I know that number is 8. Now if I do this, I've made a mistake by just putting an 8 in there. Because this assumes that they did the whole job starting at the same time and continuing to work, right? Does that make sense? But what really happened here? So Biff started at 8, Buffy joined him at 9. So what do I do about that? Because this is the number, it says 8 hours working together, right? You can paint the house at 8 hours. Okay, so 8 hours working together, they can paint a whole house. Wait a minute, I did this right away. What time will they be done? So if I did this, if 8 hours working together, what would I be finding right here? I would be finding Barbie's what? Kind of the one over that would be the rate. This would be how long it would take her to complete the whole project, right? So if I want, I could do this, but this is not really the question I need to be answering, but it is something that I could do. So right here, if it were me, I would multiply by 20x. I think this is the way I did it. And when I distribute, because the common denominator, and I can do that because it's an equation, and when I distribute that through, I get 8x, distribute into there, plus 160 equals 20x, so 12x equals 160, and I am finding, what does that end up being, 40 thirds? So x is 40 thirds. And now that I know how long, whatever that is, 13 1/3, now that I know how long it would have taken Barbie to paint the whole house, I can go back and say, all right, if Biff's rate is 1/20th and Barbie's rate is 40 thirds, that's how basically how long, if I solved that equation, I would get a time equals 8. That confirms this. But I don't want that. I want to know, okay, it would take them 8 hours working together, but what time would they be done if Biff began at 8 and Barbie joined them an hour later? So what could I do to tweak this? And again, you can put those T's on the top if you want. What could I do to tweak this to find out how long it would take them? T minus 1. Because Barbie ended up working 1 hour less. Now there are other ways to go about doing this, but to me, this is kind of a straightforward way of saying, okay, let me find, I know how long working together, they could paint the whole house, start to finish. So I'm finding how long it would take Barbie to work alone, and if she can do the whole house alone, now I can figure out the time it takes them if Biff gets a head start on the house. And if you were solving that equation over there, and by the way, if I ever told you, like, what would you do if I said, you started painting at 8, and he joined, say I said Barbie joined him at 8:45. Are you gonna go T minus 45? Why not? 3/4, because I can't mix minutes and hours, right? And all these are in hours. Okay, so make sure you're careful about that. But in this one, what could you do right here? I don't really love the way that looks, because you have a fraction within a fraction. So what, I could do a couple different things here. Yeah, why not? So if I'm dividing by 40 thirds, why don't you multiply by 3/40? And if I multiply by 3/40, it basically just gives me 3t minus 3 over 40, right? So I would probably do that, and then I could multiply through by a, which would be 40. So now I can just multiply through by 40. And that would give me 2t, 40 is completely canceled now, and 3t minus 3. And so at this point, I'm just 43/5. So 8 and 3/5 of an hour. And what is 8 and 3? What's 3/5 of an hour? What do you do? So you multiply it by 60. So if I have 3/5 of an hour and I want minutes, multiply by that part by 60, and it gives you 36 minutes. So if I start at 8, and I add 8 hours and 36 minutes to it, when do I finish? Do we say 16:36? Maybe in the military, but in most people's life, I started at 8 a.m. How do I figure out what p.m. time this is?
You subtract 12.
Subtract the 12 from that, and it gives me 4:36 p.m. Y'all with me? Listen, you've only known me a couple months, but when I put can be tricky, I mean, it's possible those show up as test questions, but the most of the time I make a bonus question out of that. But it's totally possible for the concepts to be in there and the concepts to be asked. But and there are other ways to go about this that might be a little bit more simple, but this is more direct and less original. I'm using what I know to figure out the rate. Like if they start at the same time, worked 8 hours, find the rate, and then use the rate to figure out what the time would be if they started at different times. That's 28. Review number 2, number 15. All right, so now that we've seen one of these, let's see if we can do a little bit better with it. Of the 2 ways I went about doing these, do you like being multiplied through by a common denominator, or do you just rather do find a common denominator and add them?
Multiple through.
Anybody feel differently? Anybody like finding a common denominator? Because if you do, stick with what you know. There's no use reinventing a wheel if you're getting something right. Now I look at this and I see a fraction inside of a fraction inside of a fraction. That's a little bit above my pay grade right now, so I'm going to slow it down and just look at the first inside part. So that's a fraction inside of a fraction. Now what do you see as the common denominator of these terms right here? 2y. So ignore everything else. Multiply by a 2y over a 2y. So everything else is coming over. 2y over x minus everything else is coming over. So what happens when I distribute that in? What do you get? 6y.
I see.
And then when you, the y's cancel, and then -2 over, what happens? You multiply this times this. xy. 2's cancel, xy. All right, looks better already. Now, if I gave you that, what do you see as is the common denominator? Yeah, because I've got an x, an xy, an x, and a 1. So xy. So I'm going to come over here, do the same process again. Multiply the top and the bottom by an xy. And again, why can I do that? Because I'm multiplying by 1. So I'm changing the look, but not the value. So now when I distribute it in, what do I get? Over here on the left. 2y squared. Here, xy's cancel, and I get what? Do you see how I change the signs? Minus 6y plus 2. And you got to really be careful, because if I mess that part up, it's probably not going to factor. And if it doesn't factor because of a mistake you made, there's a chance more won't cancel. In this case, I'm not sure that matters. So, and then here, what happens when I distribute that in? xy squared minus y. Now I have a question for you. Would you bother factoring this? Tell me why not.
Because one of the binomials on the top is going to have a 2 in front of it, and there's no 2 on the denominator.
That's true, but what if the other one didn't have a 2?
There's no x.
Oh, there's no x in the numerator.
Yeah, that's what, now, it is true, like if I factored this, if it did factor, now I can pull a 2 out of this,
Oh, yeah.
and in that case, there would not be a 2 at all, but y squared minus 3y plus 1 doesn't factor. But even, let's just say it did. Right here, even if I take a y out of this, I'm still left with a what? An x in the binomial. And there's no x in the binomials up here. So whether this factors or not is irrelevant. It's not going to cancel with anything. And if it doesn't cancel, if you can see that, then don't bother factoring it. Because again, simplify means PEMDAS, and there's no f. There's no glory in factoring. We factor for 3 reasons. You're told to, we're trying to solve, or possibly divide. And if you're not doing any of those 3 things, or can't do those 3 things, we don't bother just because it's special or something. All right, that was 15. You talk about distance, rate, and time problems. Is anybody here, be honest with me, does anybody in here love the table method? Like, you're like, man, I still wear that table method out. I set it up. I feel good about it. I'm getting them right. Does anybody? That's generally my thought on distance, rate, time. Is I have had a handful of people in 28 years say, Mr. Hurry, I can kill it with the table method. And they do. And that's awesome. It impacted them when they learned that in 7th grade, or 8th grade. My normal experience is it goes in one ear and out the other, and it's gone. Well, it wasn't lasting. But you know what does last? What's the equation for distance, rate, and time?
Distance equals rate times time.
And I would be willing to bet right now that everybody knew that in here. So write it. If I see a distance, rate, time problem, I am going to write distance equals rate times time. And then, to remind myself that this is not anything special having d by itself, it possibly could have t by itself, which would be time equals distance over r, or possibly even r by itself, which would be distance over time. Which means I can get these three equations without having to really know anything. And then the other two things that I've told you I remember are what? You remember them? The total distance is the sum of the first plus the sum of the second, and the total time is the sum of the first and the sum, and that, unless there's three of them, and then it'd be the sum of the first three. And then like we know the substitution method, right? We know that substitution says if t equals d over r, then anywhere I see a t, I can put a d over r. So if you had an equation that gave you like maybe total time, but nothing about the other times, then keep the total time and replace the other times with d over r. Do that. And if you didn't know the total time, you could replace that with total distance over average rate. You can do that because times are d over r's. On the distance, let's just say you didn't know anything about distance except maybe the total distance. But you were given a whole bunch of stuff about rate and time. Well, I can replace that distance with rate and time. I can replace that distance with rate and time. And if I know total distance, great, keep it. If I don't, replace that with rate and time. Now you guys do know that, like, if I'm talking about D1, then I'm talking about R1, T1 that goes with it. If I'm talking about D2, R2, T2 goes with it. But if I'm talking about total distance, total time is not total rate. You don't add the rates. It's something in between them, right? If I drive 50 miles an hour to Auburn and 100 miles an hour back, I didn't drive an average of 150, right? It's somewhere in the middle. Are you with me? So that somewhere in the middle is like the weight, we call it a weighted average. It's not always a pure average, like a mean, like you learned Adam divide by 2. It doesn't always work that way. But sometimes it's something in between there. But this allows me all kinds of reasons always to substitute. And if you do that and then write down what you know, usually like you'll start reading the problem and you'll be like, okay, I know R1, great. I know R2, great. I know total time, great. And I know D1, and D2, great. What do I do with those? Well, I would look at that and go, well, I know total time, so maybe I use this equation, but I don't know these two. But that's okay, because time is D over R. So if I kept the total time part in there, I've got that and that, and I've got this. Maybe I don't know the D2. And the one thing I'm missing, I'm like, oh sweet, I've got an equation, I'm ready to go. But it's about identifying what you have and finding a way to fit it in there. Maybe I know total distance, which means I probably know D2, if I know that in D1. Let's just say I had something like this. And I go, well, I know all three distances, but plugging those in there doesn't really help me solve for stuff. Maybe I'm looking for T1, right? Maybe I'm like, I don't know, what is T1? But look, if I go, well, if I know total distance, maybe I keep that, and maybe I replace the distance with rate time. So I'm like, okay, I know total distance, I know the first rate, I know the second rate, I know the total time. Well, if you know total time, how can I find say T1? What can I do with T2? Subtract it. So couldn't I say, all right, the other time is just the total time minus T1. That would be the other time. And again, I've got that. So now I'm down to just one variable that's missing. That's the whole goal, is to try to set these up in a way that I know everything. And this does not fail me. It doesn't. And then I don't have to man, it'd be one thing if we took a class. What if this class was distant trade time class? Well, if we studied this all year long, and we're like, okay, today we're doing this kind of distant trade time, that would be different. Maybe it's worth having a strategy for each and every one. But man, my brain gets full. I don't know about yours, but it gets full, and I'd rather just have a map that I could throw in the back seat of my car, and just if I ever need it, it's there. And this is my map. Those original equations that I wrote down, and then I guess the one lone exception would be when there's two things that make up rate, like airspeed, wind speed, or currents. And if that's the case, I just take this thing and I break my rate up into the canoe speed plus the water speed or something like that. And we talked about going upstream and downstream. Remember that? That would be the one exception, but I don't think we even talked about that in this chapter. So, and then I did tell you so anyway, if I'm rambling, sorry, but I did tell you one little trick. And I said, if you're ever asked average rate and the distances for each individual rate are the same, what's a shortcut? 2 times the product of the rates over the sum of the rates. Did I mention in a video, or were you here, me showing you why that worked? Here's your distance. Because T, right, distance, rate times time, because T is D over R, right? I've got total distance over average rate equals D1 over R1, and then D2 over R2, right? What happens if the distances are the same? Then they're both the same as D1. D1 is equal to D2, right? Same distance? Then what would the total be? 2D1? Does that make sense? Well, if they all have D's in them, what would happen if I multiplied both sides by 1 over D1? What happens? What happens? The D1s all cancel, leaving me this. 2 over average rate equals 1 over R1 plus 1 over R2. You with me on that? Now, what would happen if I took that equation how would you solve for this? Pretend there's other numbers in there. Like, what would you do if you were solving for that x or that variable? This is what we've been doing most of this chapter. Like, if you have an equation, it's got fractions, what could you multiply through by? What would be the common denominator here? R, right? So R average times R1 times R2 all the way through. Check it out. Here, R average cancels, and I get 2 times R1, R2. Here the R1 cancels, and I get R average, R2. Here the R2 cancels, and I get R average, R1. Now remember, I'm trying to solve for R average. So how do I solve for R average right there? You factor it out. And then what would I do next? Divide by R1 plus R2. So the average rate is 2 times the product over the sum. And that's a great little formula to have. You don't have to prove it, but if you know that, it's a great little formula to have. But it only works when what? When the two distances there and back, or first leg, second leg, are exactly the same distance. Anybody remember what you do if they're the same times? Then what do you do for average rate? Like if I drove for like 70 miles an hour for an hour, and then 50 miles an hour for an hour, then how do you find the average rate?
You just add it up.
You see, that's a mean, like an arithmetic mean. You average them up, divide by 2, add them, divide by 2. But when the distance are the same, it changes. What else? Anybody else? We got 10 minutes. Anybody? Feeling a little bit better? It's a lot on this test. And again, there's a lot of ways to get careless. I actually rewrote the test this year. And I took some problems that were formerly really difficult. Like people would make a mistake in the first step and it would just be, you're done. And I broke them up into 2 parts so I could really test the parts separately. So I'd like to believe the scores will be a little bit higher where one mistake won't cost you as much. But there are still, it's a lot of stuff going on. Negative exponents, multiplying, dividing, word problems, all kinds of stuff. Yeah. On the second review? No, first review.
It's a little one.
That one?
It's like the one we already did.
This one right here? Okay. So, do any of y'all's parents know Twinkle Kavanaugh? Girl I used to know from college, but she's like into politics and stuff. I think she's like Republican chair person in the state of Alabama or whatever. Anyway, so that's a real person. And I knew a girl in college called named Muffin Moncrief. Given name, not a nickname. Doesn't she? She's really bright too. There you go. All right, so what this says is that she can cut a yard in 3 hours. So I'm giving you her time, but I'm also giving her what? Her rate is I can cut 1/3 of the yard per hour per unit of time. So I could say times t, or I could just say t over 3. And then it says twinkle after a mere couple tablespoons of sugar, whatever. It takes her 5 hours to cut the same yards. Again, that's a working alone time, so I'm giving you her rate. 1/5 of the yard per hour. So that would be 8t over 5. Then it says, at what time would they be finished cutting the single yard if they worked together? However, what does it say? Muffin starts at 10, Twinkle joins her at 11. So Twinkle worked less time, right? So what do I do with Twinkle's time? Subtract 1 hour. And again, I shouldn't have done so many with just 1 hour difference. I should have changed that. Again, if it's 36 minutes later, make sure you don't say minus 36, but say 36/60ths of an hour. All right, or 3/5 when you do that in there. And then at this point, I'm just finding the common denominator and multiplying through. And I would be remiss if I didn't mention, guys, if I give you a problem like this, and I ask you to do this, what do you not do? For heaven's sake, don't do this. What do you not do? Multiply by the common denominator. Why can't you? Because it's not an equation. And if I go and multiply by a random thing, I shouldn't be here. Where should I be?
The bank.
The bank, right? So I am not going to do that. I am going to go, wait, I can change the look, but not the value. So I would still find that number. That if you're multiplying through, you're probably multiplying through by what? What is that least common multiple? 21.
Squared, S squared.
Yeah, t squared, s squared, or s squared, t squared, whatever. So you're probably multiplying through by that, but just don't do that. Say, all right, I need to make the denominators 21 s squared, t squared. So I need a 7 and a 7. S squared, S squared. Now I have 21 S squared, T squared. I need a 21, 21, and an extra S, extra T. Now I have 21 S squared, T squared. I need a 3 to get the 21, T squared, T squared. Now I have 21 s squared t squared. And now I can take that 14 s squared and that negative 105 st and that 12 t squared and put it over 21 s squared t squared. And do I bother factoring that? Why not? That's right. We factor in the binomials. Now maybe if a GCF comes out, maybe. Or maybe if I can take an S out, maybe. Or a T out. But if I can't, and I can't, right? 2 and 7, 2 doesn't go into that. I don't have a common denominator there. So, and an S, T, neither an S nor T are in common. So I'm done, but I'm not going to waste time doing that here because there's no profit in it. And remember, simplify. Well, it didn't say simplify, but if it did, say simplify. There's no F in the PEMDAS. Don't go, there's an F in simplify. Don't do that. All right? Y'all with me? All right. Anybody last minute? Okay. Well, good luck.